Welcome to The Sleepy Scientist. It's lovely to have you here. Before we begin, I'd love to know, where in the world are you listening from tonight? Maybe a quiet bedroom, a drowsy train ride, or a cozy couch with a warm cup of tea. Wherever you are, I hope you're comfortable, safe, and ready to gently drift into thought. If you enjoy these soft, relaxing explorations and would like to hear more, a like and subscribe helps this sleepy little channel float along. And to those of you already subscribed, thank you. Truly, your support means more than you know. Now, I'll do my best not to make tonight's topic so interesting that it keeps you wide awake. But if it does, at least you'll come away knowing why particles sometimes act like waves and why reality itself seems to hesitate until someone is watching. A small price to pay for a restless light. So, what is quantum physics? And why does it so often sound like the universe is making things up as it goes along? The world we know, the one we can see and touch, feels solid and predictable. Drop a teacup, it falls. Flip a coin, it lands. Close your eyes, and the moon does not vanish. But in the early 20th century, scientists began to look closer, much closer. And the deeper they peered into the workings of matter, the stranger things became. Light, they discovered, could behave like both a wave and a particle. Particles, it turned out, could exist in many places at once until they were measured. And the act of observing didn't just simply reveal what was already there, it seemed to change it. This wasn't a quirk of bad instruments or fuzzy data. It was real, repeatable, and it shattered the tidy laws of classical physics that had held for centuries. Quantum physics wasn't just a new branch of science, it was a new way of seeing reality. A shimmering world where certainty is replaced by probability and cause doesn't always lead neatly into effect. In this video, we'll wander gently through that strange landscape. There's no need to master every equation or remember every name. We'll move slowly, softly, one mystery at a time. From the first puzzles that nudge scientists off their classical perch to the unanswered questions that still keep physicists awake in the small hours. So tuck yourself in, let your breathing slow, and let's begin our journey into a world where even emptiness is not truly empty, and where everything you thought you knew about reality is only probably true. At the turn of the 20th century, physics seems nearly complete. The laws of motion were understood. Thermodynamics was tidy, and light fit neatly into the framework of electromagnetic theory. It was a golden age of certainty. Some scientists even believed the great questions were already answered. Only a few small oddities remained, like dust in the corners of a well-spec'd room. One of those dusty corners involved a simple question. What happens when you heat something up? Warm a piece of metal or a lump of coal, it glows. First red, then orange, then white, depending on its temperature. This glow, called black body radiation, comes from how objects emit electromagnetic waves when heated. It was easy to see, and it seemed simple enough to explain, yet the math refused to behave. Using the well-known equations of classical physics, scientists predicted something absurd. As temperature rose, a black body should pour out more and more energy at shorter wavelengths, especially in the ultraviolet range. The result? An impossible infinity of energy. A prediction so ridiculous, it was nicknamed the ultraviolet catastrophe. No amount of adjusting the formulas could fix it. Simply, reality didn't match the theory. Something was missing. Enter Max Planck. In 1899, this careful German physicist not known for being a rebel, decided to take a different approach. He still believed in the classical worldview, but he was practical. He fixed the problem with a small, radical idea. What if energy didn't come in a smooth, continuous flow, but in tiny, discrete packets? Or what if energy came in tiny, indivisible packets like coins you can't split in half? These packets would be the smallest possible units of energy. Planck called them quanta. This was a big change from the old ideal that energy flowed smoothly like water. Instead, energy would come in little steps, with each step sized depending on the radiation's frequency. Planck even created a special number, now called Planck's constant, to measure the size of these packets. It was extremely small but worked perfectly in the math. When he used this idea in his equation, something amazing happened. The infinity energy problem disappeared. The math now matched the real world. Planck had solved the ultraviolet catastrophe. But even then, Planck didn't fully believe it. He thought it was just a clever math trick, not how the universe really worked. He expected future scientists to find a better explanation without such strange ideas. What he didn't know was that this trick will become the foundation of quantum theory. His idea that energy comes in packets would later challenge much of what old physics believed. At the time, it didn't feel like a revolution. Just a side note. Planck wasn't trying to change physics. He only wanted the math to make sense. But by introducing quantization, he had started a slow burning change that would completely reshape our understanding of light, matter, and reality. This quiet beginning in a small paper in 1900 made no big announcements, just a small constant, a new way of thinking about energy, and a neat solution to a stubborn problem. From that moment, physics would never again feel finished. By the early 1900s, scientists thought light was well understood. Thanks to James Maxwell's equations, they knew light behaved like a wave, a ripple in the electromagnetic field. It could bend, bounce, spread out, and interfere like any proper wave. And after Planck's idea of energy quanta, most scientists assumed things would settle into a new, slightly updated understanding. But then came a strange puzzle involving metal, light, and unexpected results. It was called the electrophotoelectric effect. Here is how it worked. When you shine light on a metal surface, electrons can be knocked out of the metal. Logic seemed simple enough. Light gives energy, and that energy takes out electrons. According to wave theory, if you made the light brighter, the electrons should get more energy. A stronger wave should take electrons free more easily. That's what scientists expected. But experiments showed something very different. Making the light brighter didn't always increase the electron's energy. A most important factor was the frequency of the light color. If the light cut too low, even the brightest beam did nothing. No electrons came out. But if the frequency was high enough, even a faint light could easily knock electrons free. The cutoff point would be sharp. It made no sense in classical wave theory. This little inconsistency became a big mystery. In 1905, his miracle year, Einstein published a paper to explain it. His bold idea. Maybe light wasn't just a wave. Maybe in some situations, it behaved like a particle of a small packet of energy, moving in a straight line. He called these packets quantums of light, later named photons. Each photon carried an amount of energy set by its frequency. If a photon had enough energy, it could knock an electron loose. If it didn't, no number of photons, no matter how bright the light, could do it. It was like trying to open a locked door with the keys that didn't fit. More keys wouldn't help. You needed the right one. His idea built on Planck's work, but went further. He said light was actually made of these packets, not just as a calculation trick, but as a real fact about nature. This was revelatory, and many scientists didn't like it. Light clearly acted like a wave, bending, spanning, and interfering like any proper wave. How could it also be a particle? Einstein didn't deny the wave fight. Instead, he said light was both a wave and a particle, depending on how you observed it. This wave-particle duality wasn't just a trick of perception. It was a basic fact about light. Look, when the window shrink, its ripples like a wave, scattering of depths. But could he zoomed far enough? You see tiny photons, each with its own frequency, colliding with atoms and changing them. In the normal world, something is either a particle or a wave, never both. But in quantum worldviews, as you hit faster in the Bishop are different. And yes, but Hurd didn't have to.